You know, your body is talking constantly. Through this incredible symphony of tiny electrical signals, your heart, your brain, your muscles, they're all telling a story about your health. But what happens when that story gets, well, lost in the static? So, let's dive into the really complex world of biosignals and the huge challenge of cleaning them up.
So, here's the game plan. We'll start by tuning into our body's electrical symphony. Then we're going to meet the villain of our story, noise. We'll zero in on the massive challenge of listening to brainwaves on the go. Introduce the high-tech heroes, the algorithms designed to fix it. See how they stack up in a head-to-head test. And finally, explore what all this means for the future of medicine.
All right, let's kick things off with the basics. It might sound a little bit sci-fi, but our bodies are fundamentally electrical. Every single heartbeat, every thought you have, it generates this tiny electrical pulse that we can actually measure. This is literally the language our bodies speak.
Okay, take a look at this. This is what we want to see. A perfect ECG signal. It's clean, it's clear, it's the story of a single, perfect heartbeat. This is the ideal. But here's the thing. In the real world, getting a signal this pure is almost impossible because this beautiful, simple story can so easily get buried in noise.
So there's an official name for this stuff, of course. We call them biosignals. And it doesn't matter if it's an ECG from the heart or an EEG from the brain. This is the raw data, the ground truth that doctors and scientists use to figure out what's going on inside of us.
And that right there brings us to the central problem. If these biosignals are the heroes of our story, well, you know, every good story needs a villain, right? In our case, the villain has a name: artifacts. It's really just a fancy technical term for noise.
And here's why these artifacts are such a huge deal. Biosignals are unbelievably faint. I mean, we are talking microvolts. That means they can get completely drowned out by any other electrical noise around. And if that happens, the signal gets distorted and could even lead to a totally wrong diagnosis.
So where does all this junk come from? You'd be surprised. It can literally be the electrical wiring in the walls of the room. This creates a constant 50 or 60 hertz hum, we call it power line interference, and it can just completely take over a recording. But get this, the noise isn't always coming from the outside. Sometimes the call is coming from inside the house. I mean, something as natural as the patient just breathing can create noise. It's called baseline wander, and it makes the whole signal drift up and down, which is a real headache to read accurately.
And believe me, those are just two examples. The sources of noise are literally everywhere. It could be the patient's own muscles twitching, an electrode that's not stuck on perfectly, or just the person moving around. All of it can corrupt the data we're desperately trying to see.
Okay, so we've seen how noise can be a pain even when things are pretty stable. But now, let's crank the difficulty up to 11. What if we try to listen to brainwaves and EEG, not in some quiet, sterile lab, but out in the real world while people are just living their lives? This is the cutting edge, and they call it pervasive EEG.
And the whole point of this, as this quote lays out, is to see what's happening inside someone's brain while they're in their own element. I mean, just think about it. Imagine studying a child's brain activity while they're playing at home, not strapped to a chair in some scary lab. You'd get such a truer picture of what's really going on. But wow, the challenge is just enormous. In a traditional lab, you're told, don't move a muscle. Out in the wild, you're walking, talking, living. And remember what we just said? Every single movement creates an artifact. So the data you get is just, it's a mess. It's full of huge, random, unpredictable noise. So how on earth do you solve a problem that's this messy? You can't just tell people to stop moving, right? The solution has to be way smarter. It's all in the software, in some incredibly clever signal processing. So it's time to bring on the heroes of our story, the algorithms. To crack this problem, researchers developed two brand new hybrid algorithms. They've got these techie names, WPT-ICA and WPT-EMD. The best way to think of them is like a high-tech cleanup crew. Their only job is to go into that noisy signal and surgically separate the real brainwave from all the junk.
So how do they actually do that? It feels a little like digital magic, but we can break it down into a simple three-step process. First, they take the messy signal and just break it all apart into its different frequency components. Then, step 2, they use some really clever math to figure out which of those parts are noise. And finally, step 3, they just toss out the noisy bits and rebuild the signal with only the clean parts left.
Let's zoom in a little. That first part, the WPT, it's kind of like a super powerful zoom lens that lets them isolate all the different parts of the signal.
From there, our two hero algorithms take different approaches. ICA basically assumes the noise is statistically separate from the brainwave and just pulls it out. EMD, on the other hand, is more like a detective that's been trained to spot anything that looks irregular or messy, the telltale sign of an artifact, and get rid of it.
Okay, so we've got two contenders, two potential heroes, but which one is actually better? To find out, the researchers set up a classic showdown, putting them to the test against real-world noise generated by people just moving.
All right, let's check out the results. First up, noise from a simple left-hand movement. The blue line you see is the messy, raw signal. Now, look at the top left. That's our WPT-EMD algorithm at work. See that red line? That's the cleaned-up version. It's so much smoother, right? It did a fantastic job. Now, look over at the top right at WPT-ICA. It's not so great. You can see it really struggles with those big swoops in the signal and even seems to add its own spiky noise. Not good.
Here's another one. This time, the noise is just from someone blinking their eyes. To see the winner here, look at those graphs at the bottom. They show how much noise there is at different frequencies. See that giant blue spike on the left side of both? That's the eye blink. Now look at the green line, the signal after cleaning. On the left, with WPT-EMD, that spike is almost completely gone. It just squashed it. But on the right, yeah, the other algorithm left a big chunk of that noise right in there.
And this wasn't just a one-off. When you look at the summary data for all the different kinds of noise they tested, the results are crystal clear. This chart shows how much noise was left after cleaning. So, a lower bar is better. And in every single case, that bar for WPT-EMD on the far right is the lowest. It's not even close. We have a definitive winner.
Now, this is way more than just some cool academic competition. A breakthrough like this, being able to clean up signals this well, it has massive, real-world implications to the future of medicine and really for how we understand the human body itself.
So what does this all unlock? Well, for starters, it means way more accurate diagnoses for things like heart conditions and brain disorders. It means we can finally start studying how our brains work out in the real world. It paves the way for smarter, more reliable wearable health tech. And it opens up totally new ways to research really complex conditions, like neurobiological disorders.
And here's the bottom line, the most important takeaway from all of this. That incredible future we just talked about, none of it is possible without a clean signal. The ability to filter out all that junk and actually hear what our bodies are trying to tell us, that is the absolute foundation for the future of personalized healthcare that works for you, everywhere. So it kind of leaves you with this fascinating thought, right? When our technology can finally listen to our bodies with this level of clarity, what new frontiers of human health and potential are we even going to be able to explore?